everyone, welcome back to the latest lecture session. So again, as is customary, let's look at what we have talked about in the previous session, or let's rather try to summarize that. So we in general looked at, or we spent most of the time with respect to looking at designing the buffers, right? And then we also looked at alkalinity, right? And that's something that's always present in natural systems, and that's one of the reasons you would consider it. Again, also because it's important. Why? Because it will resist a decrease in pH. Yes, that's one of the aspects. So then we end up looking at how to calculate the theoretical definition of alkalinity, and we also looked at how to calculate the practical definition, not pardon me, practical definition, the practical value, as in when you do that in the lab, what would you measure that, right? So the theoretical definition, where did we get that from? We set H2CO3 as your reference point, and again theoretical definition is valid only when only the carbonate system is the predominant system, right? And then we end up looking at all the bases present, and in this case they are going to be CO3 2 minus and HCO3 minus and OH minus, right? And subtract the other acids present, or it's only now going to be H plus here, right? So that's how we end up with the theoretical definition. Practical definition too tries to mirror the theoretical definition, as in you are trying to add acid or enough acid so that you titrate the solution to that particular endpoint of H2CO3. And as we calculate that, it's around 4.4 for a particular CO3 total, but standard methods looks at 4.5. Why is that? Because you want to also look at the carbon dioxide loss into the gaseous phase during your titrations and such. So you are trying to, in your practical definition, trying to look at how much acid am I titrating or need to be able to bring down the pH to 4.5, right? Then more or less that's the practical definition too. So first today we are going to look at those cases. So let's say when your practical definitions are not going to match what it is that you would calculate when you look at the theoretical definition, right? So let's look at what we have here. So I believe this is our particular figure, and let me write down the particular alkalinity theoretical equation. And what was that? OH minus, and what are the other bases? HCO3 minus plus 2 times CO3 2 minus. Why is that 2 times? As I go from, let's say, here to 4.5, right? This is, let's say my initial pH is 13. The CO3 2 minus can take 1 H plus here and then be transformed to HCO3 minus, which can again further take 1 more H plus and be transformed to H2CO3. So that's the reason why we are going to have 2 CO3 2 minus here and minus H plus, obviously. Again, this is theoretical definition, right? So what was the practical definition again? We just look at the amount of acid required to be added to the solution, so that you decrease the pH from your initial pH, which in my example here we are assuming 13, to come down to 4.5, right, which is the standard method defined equivalence point for H2CO3. Yes, and so that's the case. So obviously when will the practical definition, let's say alkalinity calculated due to the practical definition, not be equal to the alkalinity from your theoretical definition? So the obvious case is when the carbonate system is not the only predominant acid base system, right? So in general we look at natural waters, right, and that's the reason we more or less can get by with assuming that the carbonate system predominates any other acid base systems present in the solution. So even if there are any other acid base systems present or species present, pardon me, right, the carbonate system concentrations or the relevant species concentrations of these species of the carbonate system would be remarkably high compared to these particular other acid base systems. So in those cases we can get by with our particular theoretical definition of alkalinity, right? So but obviously if you have other acids and bases that let's say have equivalent concentrations, or in that particular ballpark or range as your carbonate system concentrations, so then what's going to happen though? Let's look at that, I guess. So but the theoretical definition of alkalinity is still going to be the same, yes, but what is your practical definition going to look at? So let's look at that, I guess. For that I ended up we are going to look at one particular example. So in that particular example, let's say I have H3PO4 not at, let's say, 0.01 molar, and also H2CO3 not at 0.01 molar, right? The previous figure that we looked at was when I believe we used Vimitech to be able to come up with that, and we considered, I believe, only H2CO3 to be present in the system and at 0.01 molar if my memory serves me right. But now we are going to look at system when there is another acid base system present, in this case the phosphoric acid, and at concentrations that are similar to your particular carbonate system. Let's go back to Vimintek now, right? So how do I get that done? Let me first identify the relevant species here, right? So what are the species here? And they are going to be H3PO4, H2PO4 minus, HPO4 2 minus, PO4 3 minus, and then the carbonate system. This is from the phosphoric acid base conjugate acid base systems, H3, H2, H and PO4, and the relevant charge obviously, right? And here now we have H2CO3, HCO3 minus and CO3 2 minus, and we are obviously always going to have our H plus and OH minus, right? So in this case the components that we usually end up choosing, what are they? They are going to be H plus and the most deprotonated form CO3 2 minus and PO4 3 minus, right? So what is H total going to be? So it's going to be due to these two particular solutions initially. So that's going to be 3 times H3PO4 naught. Why is that? You know, from Tableau and component balance you can look at that, but 3 H3, right? 3 protons here, and again 2 times of H2CO3 naught. Again this is from the formation equations or the component balance equations, you can come up with that, but because we have had considerable practice in that regard, I am skipping those steps. So the H total is now going to be 0.05 molal, right? And same case now CO3 total, what is that going to be equal to? It's going to be equal to H2CO3 naught, meaning that's equal to 0.01 molal, and PO4, which is the last component total, what is that equal to? The only contribution is due to H3PO4, so that's equal to H3PO4 naught, and that's equal to 0.01 molar. So what do I need to plug in? I need to plug in H total 0.05, CO3 total 0.01, PO4 total and 0.01. Again here my particular what we say objective is to be able to calculate or come up with a graph where I have pH on the x-axis and all the concentrations on this what do we say y-axis, right? I am trying to get the speciation system. So how do I do that? I can look at the titrations tab, right, in my Vimintek, or because we are just looking at pH, I can also look at the sweep option, right? And I am going to look at the sweep option, and let's look at how to get this done. And let's go back to Vimintek here, right? So what do we have here? I am going to choose H. Where is H here, please? A, B, C, D, E, F, G, H. Did I? Okay, H. Okay, and now we need to plug in that at 0.05, right? And what's the value here? 0.05. And now I am going to add that to the list. And now next I am going to look at CO3 total. And where is that? That's here. And that we know is 0.01, right? And I am going to add that to the list. And the last component was PO4. And where is that? Here. Okay, that's here. And again that's equal in concentration to 0.01. So I am going to add that to the list. To be on the safer side, I am going to check what I have here. So as you see here, we have H total is 0.05, CO3 total is 0.01, and which is similar in concentration to the PO4 total, right? I am going back to the main menu. So I am going to go to the multi-problem or sweep menu here, right? And now I am going to use sweep where one parameter is varied. So here you have different parameters which can be varied, but for now I am only going to look at pH. So I need to calculate the number of problems. So let's calculate that. Start value, I know I am going to have 0, right? And increment between values to have a relatively continuous distribution of the relevant data points. I am going to look at 0.25, right? So I need to calculate the number of problems. So let's just try to do a minor calculation here. Let's say so 0.25, meaning there are going to be 4 per pH, 4 into 14, 40 plus 14, 56, and that should also include your 0. So 57 iterations, I guess, right? So, number of problems I am stating that as 57 to go from pH 0 to pH 14 with an increment of 0.25 each time. And what do I need here? So, the present selection is already pH, which is going to be my x axis later on, and now I am going to choose CO3 2 minus. I am also going to choose PO4 3 minus. So, I am going to choose all the relevant conjugate acids and bases, right. So, I am just going by the relevant list that popped up here when I chose those components. How did we get this list? Because you chose those components here, H2PO4 minus, H3PO4, HCO3 minus, and HPO4 2 minus. Let me check if we have all the relevant aspects. So, 3 plus 4 7, right, diprotic and triprotic acid. So, 3 species CO3 2 minus. Okay, 1 2 3 4 5 6 and 7. So, I am done with that. So, save and back, and now let us run vmintek. So, the first aspect is obviously going to be at pH equal to 0, and so here I can individually choose, right, and this particular option, what is this select problem number. So, that is 57. So, 57, if our calculation was right, it should end up with pH 14. That is what we see here, right. So, we have different values. So, at pH, let us say, let us choose a random value of 3. You would expect most of it to be present as H2CO3, and that is what you see here. Let us say species distribution, right. So, at pH of 3.2, what would CO3 2 minus usually be present as? Because the pKa 1 is 6.3, everything would be present as its protonated form. So, that is why you see that 99.9% of CO3 is present as H2CO3, and very little is present as HCO3 minus. So, just for sake of understanding where we are, let us try to see what it would be at around pH 4.5, which is our end point, right. Okay, looks like I need to go further down. Okay, that is close enough now for me, or let me go further down, 20 and then 18 pardon me, 19, right. So, let us look at view species distribution now. So, yeah, this is the relevant species distribution, and why did I choose pH 4.5? Because I wanted to look at the relevant distribution for CO3 2 minus at the equivalence point we discussed earlier, right. So, we see that almost all the HCO3 minus is consumed, but still you still have some HCO3 minus, or 1.5%, and 98.5% is present as H2CO3. This is at that pH 4. And similarly, for the pKa values, we know that for phosphoric acid they are 2.3, 6.8 or 6.3 and 10.3. So, you can calculate them accordingly, I guess, right. So, because we looked at pH of 4.5, we see that most of it should be present as H2PO4 minus, because the pKa 1 is 2.3, right. So, that is what you see here, 99% is present as H2PO4 minus, yes. Again, so we are going to go back to the output menu, and I am going to say selected sweep results. This will give me a better idea, obviously. So, with pH, how is CO3 2 minus concentration going to change? It is obviously going to increase, and that is what you are going to see here, right. And that is what you see here, and the total was 0.01. So, which is 10 power minus 2, and that is what you see here, right. The maximum can be 0.01 here. And same case with H3PO4, what would you expect here? Initial was 0.01 at pH 0. As we keep increasing the pH, what do you see here? We see that it is decreasing, right. So, that is what you see here. Anyway, so I am going to say print to Excel, and then to save time I end up drawing the graph. So, let us go back to our particular system here. Let me see where I have the graph. So, here is the graph. So, how did we end up with that? We end up with this graph. I just plotted the relevant values from those sweep results. So, let us try to understand the system here and try to look at the carbonate system first, H2CO3, and that is here, and you see that decreasing, and so obviously the pKa value is around 6.3, right, and then HCO3 minus, and where is that? That is around here, and you see that that is increasing while H2CO3 is decreasing, right, and obviously at the point at which both the concentration are equal, that is going to be the pKa 1, which for your H2CO3 system, what are the pKa values? pKa values, the first one is 6.3, the second one is around 10.3, and what is it for your phosphoric acid system, H3PO4? it should be around 2.3, 6.3 or 6.7, I am not sure, and then I think around 11, these are approximate values. Okay. So, let us look at this system again, and now we are going to look at CO3 2 minus, and that is out here. So, around pKa of 10.3, right, 10.3 is the pKa 2. You see that it is equal in concentration to HCO3 minus. Yes. Anyhow, we understood that carbonate system, and then moving on to the phosphate system, what do we have here? H3PO4, where is that here? That is the orange. So, that is here, and as you see that the pKa is 2.3. So, it has this particular pKa here, and then you see HPO4 minus. So, as we looked at earlier at 4.5, all of it would be present as your H2PO4 minus, right, and that is what we looked at here. So, again now I think you get the trend. So, I think what are we trying to look at now? We are trying to look at pH 4.5 because that is our titration endpoint, and let us say initially we said our titration was starting at pH 3 or 13, pardon me. I said that we are assuming that the solution starts at pH 13. So, again let us try to recap what we are up to, so that we do not lose track of what we are trying to do here. So, we are trying to look at those cases when the theoretical definition of alkalinity would not be the same as what you would measure in the lab, right. In the lab, what do? You add acid or titrate with acid to decrease the pH till 4.5 and calculate the amount of acid. And when will that work fine, or when will both of the relevant numbers be similar? When carbonate system is the only acid base system present in considerable quantities anyway. But let us say if we have a solution where we have other what we say acid base species, in this case or example we looked at the phosphoric acid. So, we are trying to analyze how would the system change, or how would it behave. So, again what we are trying to look at was earlier only CO3 2 minus, right. Where is CO3 2 minus? Yes, CO3 2 minus, and HCO3 minus can take up the protons as you are going from pH 13 to pH 4.5, right. But now what are the other species that can also consume your proton? You have PO4 3 minus here, right. This is at your pH 13. So, you have PO4 3 minus that can consume your proton, right. And what else would you have? You would also have HPO4 2 minus. Where is that here? So, HPO4 2 minus 2 can consume your proton, right. And you can also obviously have your H2PO4 minus. Where is that? That is blue. This particular species 2 consuming your proton as you try to bring down the pH from 13 to 4. Earlier only the pardon me, what was it? CO3 2 minus and HCO3 minus were what we had to look at, right. But now we also need to consider the other conjugate base species of the phosphoric acid. So, these need to be taken into account, right. So, earlier the only species that could neutralize your particular acid or the proton were CO3 2 minus and HCO3 minus. But now what do you have? You have the other conjugate base species, they are PO4 3 minus, and what are they? HPO4 2 minus and H2PO4 minus, right. So, let us look at, let us say how the equations would change, let us say in this particular or kind of a system. Let me try to write that down right here, so that hopefully we can get some particular case. So, the alkalinity equation, if you are trying to calculate it, again this is not the theoretical definition, but let us just try to calculate that or estimate it. Let us see how is it what is it going to be. So, we are going to write down our usual formula first, which would have the carbonate species and OH minus and such, right, HCO3 minus plus 2 times CO3 2 minus, right. So, this is something that we know from our theoretical definition itself, but we now additionally have the phosphoric system. Let us try to plug that in, I guess. So, here we know that we need to consider H3PO4 and what else, plus or minus we will decide later, H2PO4 minus, HPO4 2 minus, right, and PO4 3 minus. So, obviously which would be the positive and which would be the negative? Obviously, the bases would be the positive, right, those which can neutralize your acid. So, positive would be the bases, right, and the negative would be the acids, right. So, that is one case, and then we need to look at what is the coefficient going to be. So, in general we can assume that let us say it is PO4 3 minus can take in 3 protons and go to its protonated state of H3PO4. So, I can say that the coefficient is going to be 3, right, but that is not the case here. Why is that? Because we are stopping the titration at 4.5 itself, right. Let us say I am starting from 13, I am going from here to here, but I am stopping the titration at this particular point, and at this particular point in or the pH 4.5, what is this present as it's only present as H2PO4, right. So it's not going all the way down or to its not down, pardon me, all the way protonating to HPO4, H3PO4. That's what I'm trying to point out here. So here it's only going to be able to take 2 protons here, right, and here it's only going to be equal to 1, and this is my reference here, right, then this is going to be 0 here. Hopefully that makes sense. And again, why is that? Our alkalinity titration endpoint is 4.5, right. So we are only concerned with those particular bases which would be present when we are, or which would come into play when we are going or bringing down the pH to 4.5, right. So if I had, let us say, my titration endpoint to be pH 1, then I could have written 3PO4 3 minus, 2 HPO4 2 minus, 1 and blah blah and so on. But here I am still concerned with the H2CO3 equivalence point. So PO4 3 minus, what can it transform into? It can first transform into HPO4 2 minus, right, and then H2PO4 minus. It can only take 2 protons. It can't go all the way down to H3PO4 because the pK is 2.3 here, right. So that's the difference that we see here. Makes sense, hopefully, right. Again, so here again, now if you measure the relevant theoretical, not measure the theoretical, pardon me, measure the practical value of alkalinity. So it should hopefully be equal to what we just came up with here, right. Hopefully that makes sense. Yes. Again, it's nothing but you just want to consider those bases that would come into play in your pH range of interest. And here our pH range of interest is not 14 to 0, but let us say 14 to pH of 4.5, right. So if it was 14 to 0, then I would have taken all the other coefficients, as in 3 times of PO4 3 minus or 2 times of HPO4 2 minus and so on. But here I am stopping my titration at only 4.5. At that particular pH 4.5, we see that the relevant speciation for the phosphoric system, it just ends with HPO4 2 minus, which is my H2PO4 minus, pardon me, which is my reference. Yes. So that's why PO4 3 minus can only take 2 protons to change state, not state, pardon me, to move to its conjugate acid, what do we say, species, which is H2PO4 minus. Because why is that? Again, we are only stopping our titration or at the endpoint, which is 4.5 here, right. So that's the case here. So let's move on, I guess, right. And we already looked at theoretical definitions now. We looked at the practical definitions, and we looked at when is it that both are not equal and how to be able to calculate that. Yes, we looked at that particular aspect. So now let us say we are going to move on and see how the system would change when I add a strong acid to my particular system. The second case is when I add a strong base to the system, and the third case is when I bubble carbon dioxide through my carbon dioxide gas through my particular system, right. So let us write down the theoretical definition here again. We are again just, if we are considering theoretical definition, that means we are assuming that carbonate system is the only relevant species system present here, right. And I have this particular definition here, plus CO3 2 minus into 2 times, because it can take up 2 protons. So here if I add an acid, let us say, what does that mean? It means I am adding a H plus, right. So in effect, it is going to decrease my alkalinity by, so when I increase the acid, right, it means I am increasing my H plus concentration, right, or not increasing, let us say I am adding H plus, right, I am adding H plus. So how would alkalinity decrease now? Obviously alkalinity is going to decrease because it is minus H plus, right. I am adding H plus, keep that in mind. I know that there is a minor interplay of words that I need to be careful about. I am adding H plus. By adding H plus, obviously all the other species concentrations would change and blah blah, but yes, but in effect if you are looking at it holistically, how would it change compared to initially? It would only change by the amount of H plus you are adding to the system, right. So that is what you see. And how is that going to decrease? So for 1 equivalent per liter of acid added, it is going to decrease by 1 equivalent per liter of your alkalinity. Yes. So whenever you increase or add acid by 1 equivalent per liter, your alkalinity is obviously going to decrease by 1 equivalent per liter. So that is what we see here. So but now let us say if I am looking at the condition of the base where I add OH minus, let us say, to my particular system, as in I am adding OH minus here. So as you see here, what would that lead to? It will lead to an increase in my alkalinity, right. Again, keep in mind that the alkalinity is going to change and all the other variables are going to change too. But if I am just comparing case 1, alkalinity 1 and alkalinity 2, and the only difference between 2 and 1 is that here I added some base, right, some known concentration of base. Let us say, how is that obviously going to change? So, the alkalinity of 2 is going to be equal to alkalinity of 1 plus this OH minus naught that I added to this particular solution. Yes, so that is what it means here. So, again if I add 1 equivalent per liter of OH minus, so how will my alkalinity equation change? It is going to change, it is going to increase that by 1 equivalent per liter, right, and that is what we see from this particular equation. So, that is relatively easy, alkalinity is nothing but acid neutralizing capacity more or less. So, obviously if you are adding acid, acid is more or less not more or less, it is negative alkalinity. So, you are going to decrease that, and if you are going to add a base, you are now increasing the increasing the pH and the relevant conjugate bases. So, it is going to have a positive effect on your particular alkalinity. So, again by 1 equivalent per liter we just looked at the relevant equations, but a trickier aspect would be to consider when CO2 is bubbled through your particular solution or when CO2 is in equilibrium with your particular solution, right. So, what is happening there? Let us try to understand system first. I believe we did talk about this earlier. So, CO2 in the gaseous phase, so in equilibrium with the aqueous phase can transform to H2CO3, right, H2CO3, and what will that transform to now? That can dissociate into either H plus. Okay, let me come back to this later when I try to point out what it is people are up to. So, usually people just look at this particular aspect that CO2 in equilibrium will form H2CO3, and since H2CO3 is an acid, right, and people go back to this particular case here and they look at acid, right, I am adding an acid to the system. So, people assume that the alkalinity is going to decrease. So, keep in mind that yes, H2CO3 is being added to the system. So, the pH will decrease, yes, because we are adding an acid, but would alkalinity decrease too? That is something that we need to look at, and let us see where the key lies here. So, H2CO3 can dissociate into H plus and HCO3 minus, and which can again further dissociate into H plus and CO3 2 minus, right. So, this is the key here. So, let us say if I am just looking at this particular dissociation. So, by adding H2CO3 or 1 equivalent per liter of H2CO3, I am increasing the concentration of H plus by 1 equivalent per liter and also HCO3 minus by 1 equivalent per liter, right. And so, what does that mean? So, here minus 1 and plus 1, so both of them just cancel each other out, right. Or if let us say there is a more complete dissociation, so per each equivalent of H2CO3, right, and if I am looking at this particular dissociation, let us say what is happening here for each equivalent of H2CO3 that is going to be inputted into your solution, you are going to have 2 equivalents of H plus, right, and 1 equivalent of CO3 2 minus. So, if I look at this particular case, right, what does that transform into? 2H plus, but keep in mind here that it is equivalent. So, if I look at the molar concentration, it is going to be 2 times. So, minus 2 and plus 2 of CO3 2 minus, they again cancel each other out. So, in effect when you bubble carbon dioxide through your particular system, though the pH will decrease, right, you are adding the other species like HCO3 minus or CO3 2 minus, let us say, your alkalinity is constant, right. So, this is a key take home message. So, when you bubble carbon dioxide, which is an acid, through your particular system, obviously you are adding an acid, so the pH is going to decrease, right, but the other variables too are going to be affected. And what are those variables? Obviously here they are going to be HCO3 minus and CO3 2 minus, right. So, H plus and HCO3 minus, they cancel each other out, and 2H plus and CO3 2 minus, they cancel each other out, right, or 2H plus and 2 times CO3 2 minus, they cancel each other out, and thus we end up with no change in alkalinity. Yes. So, this is the key aspect that we need to look at, because we are going to end up widely looking at the applications with respect to this particular take home message, right. So, now let us move on to one aspect, let us just try to briefly summarize what it is up to, and then we will be done for today's session, right. So, obviously until now we have looked at alkalinity, yes, and we looked at why it is important to, right, it is the acid neutralizing capacity. So, obviously conversely we are also going to talk about acidity, right, but acidity people look at different aspects. So, people call that as base neutralizing capacity, right. So you can that's easy to understand. But unlike alkalinity, people don't look at just one endpoint, they look at different endpoints depending upon what it is that you are trying to understand about your system. For example, in your alkalinity or acid neutralizing capacity, you end up at equivalence point of 4.5 and that's it, you are done with it. But for what do we say, base neutralizing capacity or acidity, right? What do people look at? They look at three particular equivalence points. One would be when you are trying to only measure the strong acids present in the solution, and the other extreme would be when you are trying to measure all the acids present in the system, and the other one, phenolphthalein acidity, in between both these particular equivalence points. So we are going to discuss this particular aspect in the next class, and for today's session I am done, and thank you.